Good afternoon. So I decided to go ahead and record this before normal class time, um, just because I tend to forget to record, and the recordings get really long when I use class time to do it. So I thought I'd try to go through it a little bit quicker for you here in case you have to go back and watch it later. Okay, so we're still talking about, like everything we've been talking about this unit is considered a polynomial function. Okay, polynomial just means it's got x raised to a power in it, um, and like there's no square roots, there's no exponents that are fractions, so there's no cube roots. There's nothing but normal positive exponents. And so there are different ways that you can classify polynomials, um, and different things that you can tell just based on the equation. So I've given you several different polynomials, right? And the first thing I want to do is talk about the degree. And the degree is just the, let me change colors here because I don't want to start in red. All right, the degree is the highest power of x. Highest power of x. So in this first example, there is no x, and so the degree is 0. In the second example here, we have an x to the first. The 1's just invisible, so the degree is 1. And then you can see the highest exponents in the other ones. You've got a 2, 3, 4, and 5. Now, even if for some reason those terms were not in order from the highest exponent down to the lowest, the highest exponent, even if it's not first, does determine the degree. And the degree determines the type. Okay, so if the degree is 0, that is actually the graph of a constant, and we will see when we look at the parent functions in a minute that that will make a horizontal line. Okay, when the degree is 1, all right, that is the equation of a line. So we say that that is linear. Okay, when the degree is 2, all right, remember those make parabolas. The name of that is quadratic. When the degree is 3, we call that a cubic function. When the degree is 4, we call that a quartic function. And just for fun, when the degree is 5, we call that a quintic function. I don't know if there's any fancy names for anything higher than that, but technically, polynomials can keep on going up in degree. They just, excuse me, they just might not have a fancy name. Okay, so then what does that tell us about the number of possible solutions? Okay, well, we looked at this when we were solving higher order polynomials. Remember that the highest power of x can tell you the number of possible solutions that you will get. So the number of possible solutions is actually the same exact number as the degree. Okay, and again, we call the degree n as a generic term. And so if we have a constant, almost always there are no solutions. Remember, solutions are the same thing as x-intercepts if we were looking at a graph. Okay, and unless the equation is y equals 0, for a constant, you will never cross the x-axis. For a linear function, lines will always cross the x-axis once. For quadratic, when you have a parabola, you don't have to cross it twice, but you can cross it up to twice. So we have two possible solutions. For x cubed, we have 3. For x to the 4th, we have 4. And for x to the 5th, we have 5. Now remember, that doesn't mean that you will actually get that many solutions. Some of them will be what we call double roots. You get the same solution twice. And if you were looking at the x-intercepts, okay, that doesn't always match up with the number of solutions you get either. All right. For the number of possible turning points, okay, you have to think about what we talked about when we were graphing some of these. Um, so like think about, um, so we have, this is a horizontal line, right? It never turns, okay? This is a linear function, all right? It never turns. This is a parabola. It turns once, okay? And then the other ones, they can turn up to a certain amount of times, but they don't have to, okay? So most cubic look like this, but they don't all have to. So the number of possible, the most that it could have is 2. For x to the fourth, remember those are your m's and your w's. So they could have up to 3 turns. And if you see a pattern here, hopefully you realize that x to the fifth could actually turn up to 4 turns. And so if I was looking for a way to remember that, it's really just the degree minus 1. Except you can't get a negative answer. So like if we did the 0 minus 1, we wouldn't get a negative answer here. Okay? And then the leading coefficient, that's just fancy terminology for the number in front of the highest power of x. Even if it's not in order, the leading coefficient is the number in front of the highest power of x. All right, if there's no power of x, then the single number is your leading coefficient. All right, and so then hopefully you can look over and see that you have a -5, a 12, a -1, a -3, and a 9. All right. Okay, so now let's take a look at, refresh our memory on our parent functions for all of our polynomials at the same time. Okay, so for a constant, all right, your parent function, you could say y equals, or f of x equals c, and c is just a number. So the graph will always be a horizontal line through whatever that number is. Okay, for a linear function, like the basic equation for all lines is y equals mx plus b. But when I'm talking about the parent function, I'm really just talking about y equals x. That means it goes through the origin, see if I can draw this, with a slope of 1. Okay? For quadratic, my parent function, that means there's no transformations, right? It still has its vertex at the origin. All right, so it's going to be your parabola with the vertex at the origin. Okay? All right, your other parent functions, your cubic, is again just x cubed, where there's no changes there, no transformations. And so it doesn't actually have any turning points. Ooh, got a little sloppy there. Try that again. It does curve through the origin, but we don't really call that a turning point in the sense that like it actually changes from increasing to decreasing, okay? Or vice versa. All right, quartic, your parent function is x to the fourth. Okay, and typically that looks like a W, but because it doesn't have anything else with it, if you were to graph it on Desmos, it would just look like a really wide parabola. Okay, but more often than not, quartic functions look like M's or W's, right? Just like for cubic, more often than not, you've got like that N shape, or that hill and that valley. Okay, but the parent functions just don't have all of those terms in it. Okay, and if you were to take the time to graph x to the fifth in Desmos, you would see it looks a lot like x to the third, except it flattens out a little bit more at the origin. Okay, but if you had a lot of other stuff, like plus x to the fourth minus 2x third, if you had a bunch of stuff out here, then you would see a lot more turns in the graph. Okay, so you do want to be familiar with your basic shapes. Okay, so now I want us to look at some end behavior patterns. Okay, and I encourage you to pause the video and do this on your own, because what you're going to do is you're going to type these functions into Desmos, and then all you're going to do is look at the end behavior. So that means you're going to say as x approaches, and then you're going to look at the left, so we'll say negative infinity, and then you can either write y or f of x, it doesn't matter to me which notation you use. You're going to say y approaches, and you're going to tell me if that end goes to positive or negative infinity. And then you're going to do the same thing when you look at the right. So you're going to say as x approaches positive infinity, what does y approach? Okay, so you're going to have to write that in for all of these problems. And I want you to, like, this is a really good time for you to pause the video, pull up Desmos, and actually type these in and look at the end behaviors. You've done this before. This should be a quick review for you. So I'm going to pause the video, and I'm going to pull up Desmos and fill this stuff in. Okay, so I hope you paused the video and try that on your own, and now you should take a minute to check your answers. Okay, and then what I want us to do is I want us to see if we notice any patterns. Okay, so I want us to look at, let's kind of see what happens when the degree is even. Okay, so remember the degree is the highest power of x. So this one has an even degree, this one has an even degree, and this one is an even degree. Okay, now find the ones that have a positive leading coefficient. Okay, so we have the even degrees marked. Now I want to look at the ones with positive leading coefficients. Okay, that's a positive one, but this one's negative, so I don't want to look at that. All right, look at their end behaviors. What do you notice? Okay, I hope you notice that they have the exact same end behavior. All right, because so let's talk about, so let's write that down. So you can see that as x approaches negative infinity, y approaches positive infinity, and as x approaches positive infinity, y still approaches positive infinity. So what that means is on the left and the right, both ends are going up. So you might want to draw yourself a little picture there. Okay, now I know I only have one that's negative. Okay, we have a negative coefficient here, but look what happens to the y value that it approaches. Okay, all right, it switches to negative infinity, and that's because the ends, if I were to draw myself a little picture, all right, you know, like x to the fourth makes that M shape, and so the ends both go down. All right, so that happens for all even degrees that have a negative leading coefficient. And the reason we're doing this is because if you learn the patterns, you'll be able to answer questions about the end behavior without actually looking at the graph. Okay, so if the exponent is even, it could be an x squared, x to the fourth, x to the sixth, x to the 16th, x to the 26th, okay, anything that's even. All right, if the leading coefficient is positive, both ends go up, and if the leading coefficient is negative, both ends go down. Okay, now let's go up here and take a look at the odd degree functions. Okay, so I'm looking for all the ones where the leading, right, the highest exponent is odd. So I've got 3 of those, and then you'll notice that if we look at their coefficients, some of them are positive and some of them are negative. Okay, so look, we have two right here that are odd and they have positive coefficients. Okay, so let's look at the end behavior. All right, they're actually exactly the same. When we look at the left side, so when as x approaches negative infinity, when we look at the left side and the degree is odd and the leading coefficient is positive, the left side will be going down. And when we look at the right side, the right side will be going up. So it'll look something like this. Okay, it doesn't matter what happens in between when you're doing end behavior, you only have to worry about the ends. Okay, so if it's odd degree and the leading coefficient is positive, your left end goes down, so your negative matches your negative, and your right end goes up, so your positive matches your positive. And then if I do the same thing for an odd degree with a negative coefficient, notice that your end behaviors switch. Okay, so when you look at the x going to the left, the y is actually going up. And then when you look at the x going to the right, the y is actually going down. So if I were to draw myself a little picture of that, the left side would be the one going up, and the right side would be the one going down. Okay, so hopefully that's a pattern that you can learn because you're going to be answering questions like the following. You might just be given a picture or just a description, and you have to decide if the degree is even or odd, then determine if the leading coefficient is positive or negative, and describe the end behavior. And you can do this in whatever order you want. So if you feel more comfortable, okay, doing the end behavior first, feel free to do that. In fact, that's what I'm going to do. So remember, when x approaches negative infinity, that means look at the left. And when x approaches positive infinity, that means look at the right. So here's my left, here's my right, and hopefully you notice they're both going down. So the y, which is the same thing as f of x, is approaching negative infinity. Well, when these are the same, right, when your end behavior is the same, it must have been an even degree function. Okay, and when they're both negative, it must have had a negative leading coefficient. Okay, all right, now when I look at number 8, all right, so remember this is the left, this is the right. When I look at the left, it is going down, and when I look at the right, it is going up. Well, if these are different than each other, this must have been an odd degree function. And if the negative is paired up with the negative infinity and the positive is paired up with the positive, this must have had a positive leading coefficient. Okay, so hopefully that is something that you can feel comfortable doing on your own. All right, moving on. Let's kind of put it all together now, and let me give you functions. And without actually looking at the graph in Desmos, you should be able to pick out the degree, the leading coefficient, tell me what type it's called, how many possible turns it could have, how many possible solutions it could have, and what the end behavior is. Okay, so I do strongly encourage you to pause this. I will do one with you to give you an idea, and then I think you should pause it, try them, and then check your answers with mine. Okay, so remember, degree is the highest power or highest exponent of x. The leading coefficient is the number in front of the highest power of x, and the degree determines the type. So this is a cubed, x cubed, so this is a cubic function. Okay, remember the number of possible turns comes from the degree minus 1, and so that would be 2 here. and the number of possible solutions equals the degree. It's the same as the degree. And so that would be 3. Okay? And then when I do my end behavior, you're going to have to write it in. You're talking about as x goes to negative infinity, so you're looking at the left, and you're telling me what does the y value do? And then you have to look at the right, so x has to approach positive infinity, and you have to tell me what the y value does. Okay, well, let's do it without a calculator. So let's go back here. This is an odd degree function, okay, with a positive coefficient. Odd degree with a positive coefficient, right, means that our end behaviors do not match each other, but when you look at the x's and the y's, negative infinity matches with negative infinity, and positive infinity matches with positive infinity. Now, you're welcome to check it in Desmos, but you should try to learn the patterns, okay? So here is where I'm going to pause the video, and I'm going to take a minute and fill in the other answers, and then you should come back. You should pause it as well and come back and check your work. All right, take a minute and check numbers 10 and 11. Okay, 10, the degree was 2, so it was quadratic. And so when you do the end behavior, remember quadratic makes a parabola. And if the leading coefficient is negative, the parabola opens down. Okay, so for your end behavior, the left and the right should both be going down. All right, and then for number 11, the degree is 1, so that's really just a line, but the leading coefficient is negative, so it's a decreasing line. So if you know enough about it without graphing it, you can do it that way. All right, it's no turns, one solution. All right, and then when you do your end behavior, the left is actually going up and the right is going down. All right, so this is an odd degree with a negative coefficient. And so remember, for odd degrees, your up and down cannot match. They have to be one of each. And then when you put it, like when you compare it to the x, they should be mixed, one positive and one negative. Okay. All right. And I'm going to pause it again and do. Okay, so I went ahead and filled in the other two, and you should definitely take the time to check your work here. For number 12, we had an odd degree with a negative leading coefficient. And so your left should be going up and your right should be going down for your end behavior. And then number 13, we had an even degree with a positive coefficient. And so the left and the right should both be going up. Okay. All right, so I'm going to stop the video here because we're going to move on to a different portion of the notes, and this is plenty long. So I'm going to stop it here and then I'll record the second part in a minute.